Hello everyone, good morning. I am Mohiuddin Ahmed and today I am here to do a presentation on advanced power factor correction with AC to DC flyback converter technology. It's for our MSc project 990A and our supervisor is Dr. Ashraf Ali Khan and our project coordinator is Dr. Mohsin Jamil and my other two groupmates are Imtiaz Reza Hamim and Muhammad Sejan Islam. Here is the outline of our overall project. First one is introduction, then flyback converter fundamentals for PFC, then design circuit, then we will do simulations and we will analyze the result, then the conclusion. Now what is power converter? It's a device or circuit that transforms electrical energy from one form to another, and typically these transformations happens by changing the voltage or currents or normally frequency to meet our requirements. And there are actually three types of converters. First one is AC to DC converters, which is actually rectifiers, and it is used in normal power supplies and battery chargers. And another one is DC to DC converters, which converts DC voltage levels to different levels, such as step up, which is called boost, and step down, buck, and step down, up down, which is buck boost configurations. And another is DC to AC converters, which is normally inverters. It converts DC to AC, such as solar inverters, UPS, and variable speed drives for motors. And here is the right side, we have shown the circuit for each types. And then flyback converter, it's a isolated converter that operates by storing energy in a transformer during the on time of a switching transistor and then transferring the energy to the output during the off time. Here is the basic circuit diagram of this flyback converter. Here the transformer is flyback transformer, which isolates the load side and input side. Then flyback converter operations, it includes several steps. First one is energy storage. In this stage, transistor, normally MOSFETs, connect input voltage to the primary winding of transformer. Then the energy transfer. When the transistor turns off, stored energy in the transformer's magnetic field induce a voltage in the secondary winding. And then the isolation. Normally transformer performs this task like provides galvanic isolation between input voltage and the output voltage. And the rectification and the filtering. Induced AC voltage in secondary winding rectified by the diode, and then it is filtered by the capacitors to produce a stable output voltage. Then the regulation. In this case, control circuit adjusts switching frequency and duty cycle of transistors to regulate voltage variations in input voltage and the load conditions. Then the power factor corrections. It's normally a technique which is used in electrical power systems to improve the ratio of real power and the apparent power. There are four types. First one is passive power factor corrections. In this case, normally we use capacitors and filters. And second types is active power factor corrections. In this case, we use active elements like boost converters or active filters. And the other one is hybrid power factor correction. It's normally a combinations of passive and active techniques. And the another one is and the last one is unity power factor, which is focuses on the achieving unity power factor like power factor 1. Then flyback AC to DC power factor corrections. Okay, this slide will be continued by others project groupmate Muhammad Sejan Islam.
Hello. Now we'll discuss the flyback AC to DC power factor correction. First of all, we want to discuss the components and the operation. there are two stages. First one is the boost converter stage, where it converts the AC input to a higher DC voltage, and second is it controls input current waveform to align with input voltage. And the next stage is flyback converter stage, where it converts the boosted DC voltage to desired DC output, and it provides a galvanic isolation through a transformer. Let's discuss about the advantages and disadvantages of this. Here, the first one, here you see that it minimizes the reactive power consumption, and there's the second one is the compliance, where it meets regulatory requirements for power factor correction. Then the versatility is that it is suitable for various applications requiring isolated DC outputs. And now take a look into the disadvantages, where we can see that it has some complexities, like integrating boost converter adds design complexity. There are issues in component selection as well, such as it is critical for achieving desired performance and efficiency. And finally, the cost. Additional components may increase the system cost. Now we'll discuss about the GaN switches, which is actually in full form we know it's gallium nitride, which is a wide bandgap semiconductor material used in power electronics for its high efficiency, high speed switching capabilities, and ability to operate at higher frequencies and temperatures compared to silicon. The features of a GaN switch: the first is high switching speed, where GaN switches can switch on and off much faster than the traditional silicon switches, enabling a higher efficiency and reduce switching losses. Then lower conduction losses, where due to its material properties, GaN offers lower on-state resistance, resulting in lower conduction losses and higher efficiency. Then its size, which is very compact. GaN devices can achieve higher power density and reduce the size of the power electronic systems due to their smaller footprint and better thermal management. Higher frequency operation. GaN switches are capable of operating at higher frequencies, making them suitable for applications requiring fast switching, such as power supplies and wireless power transfer. And the last one is temperature resilience. GaN devices can operate at higher temperatures without a significant performance degradation, enhancing the reliability in harsh environments. To perform the operation of the flyback converter, we need to know some basic fundamental equations. Firstly, we have the rectified value of the input voltage, represented as V in DC is equal to V in AC multiplied by root 2. This equation helps us to convert the AC out input voltage to its DC equivalent, which is crucial for further calculations. The next equation is the transformer transfer ratio, where N is equal to V output divided by V input. This ratio is fundamental in ensuring that the transformer steps the voltage up or down appropriately for our desired output. The next one is the duty cycle equation, where N is equal to V output multiplied by N divided by V in DC, where the proportion of time the switch is on relative to the total switching period. And finally, the PI controller transfer function, where we can see it is HS is equal to KP plus KI divided by S, where KP is the proportional gain and KI is the integral gain. This function helps us to design the control loop to ensure stable and accurate regulation of the output voltage. In a nutshell, we can say that understanding these equations is critical for optimizing the performance of our flyback converter, especially when utilizing the high frequency capabilities of GaN switches. Let's talk about the circuit. Here you can see the overall circuit. This is the basic circuit for the flyback converter. Here we can see we have an AC source which we are rectifying the AC voltage to the DC. In the second stage, we can see that we'll perform the boost operation of the power factor correction. And lastly, we are performing the flyback operation. Our main focus is on the flyback operation to isolate the load from the main circuit in order to keep it safe from any kind of disturbances.
Hello everyone, I'm Intesa Hamim. Now I'm going to explain the overall simulation and the circuit diagrams and the results and conclusion. Starting with the circuit design, here we can see a multi-output based flyback converter for power factor correction. So starting with an AC voltage source that was rectified to an DC voltage. Then, a boost converter has implemented on this circuit to perform the power factor corrections. Here, Q1 switch is used for the boost operation, which was controlled by a boost switch controller. Along with that, to obtain the multiple output for our DC appliances, we have used a flyback converter for that, and which operation is controlled by a switch, which is Q2 in this circuit, and controlled by a flyback switch controller. And here comes the design specification for the circuit. Here we have used a supply voltage of 142, and we are considering two output voltage from the flyback converter. One is 40 volt and one is 20 volt. We are considering the design parameter based on 200 word and 100 word on the output. And for the boost operation, we are aiming to have 200 volt on that. And we are using the switching frequency for both boost switch and the flyback one for 65 kilohertz. And the supply frequency is 60 hertz. Along with that, we are using an inductor with a value of 0.3 millihenry, and we are using filter capacitor, boost capacitor. And for that circuit, to have a power factor correction, we are using an inductive load on one end of the flyback converter and a resistive load on the other end of the flyback converter. So here is the simulation of the flyback converter for multiple output and for power factor correction. We have implemented this circuit on MATLAB Simulink, and here, as we can see, we have highlights the flyback converter and the two loads. The inductive load is indicated as load 1 and the resistive load is indicated as load 2. And here we have used a MOSFET switch, which is indicated as a boost switch for the boost circuit, and another MOSFET switch for the flyback operation. And here is the control circuit and feedback loop of the flyback converter along with the boost one. And the first figure, which is for the controller for flyback switch. We have compared the reference voltage with the obtained one. Then we have passed through a PI controller. Then we have limit the result of that. And we have compared that with a repeating sequence. Then we are getting switch pulse for the flyback switch. Same thing goes for the boost switch operations. And we have compared the reference voltage of 200, where we are looking for a boosted voltage of 200. So we have compared that one, um, build and controller for the boost switch operation. And here we have developed a circuit to measure the power factor, where we have taken the input voltage, which is indicated as VAC, and input current, which is indicated as IAC, And on the power factor display, which we'll see on later on, uh, what is the power factor value of the circuit. And here is the results of the simulation. This graph demonstrates the input voltage and current. The blue one is for the input current and the red one is for the input voltage of the system. So as we can see, both the current and the voltage are in phase. And as we have given 142 input voltage and we are obtaining nearly 50 ampere of the current from the source. And here's the results for the boost stage voltages and currents. Here we have obtained the 142 volt of rectified voltage and the inductive current of 50 ampere. Initially it wasn't stable, but after 0.1 second it get stable and got the 50 ampere current on that. And we have got the boosted voltage of the circuit, which is 200 volt approximately. I'm saying approximately due to the ripple voltage on that. Moving to the next slide. And here is the switching signals for the volt switch used for boost operation and the flyback operation. So here PWM1, which is indicated as boost switch, we are getting the signal which is indicated in this figure as a green color. And for the flyback operation, we are getting the signal which is indicated in this figure as the red color. And here's the results for the flyback operation, which we aimed initially to have a multi-output voltage on the flyback converter. So for the inductive load, we got the voltage which is indicated as Vout1 is 40 volt, which we have set for that circuit, and getting a current of 4 ampere on that portion of that circuit. And on the other end, for the second output, we are getting a voltage of 20 volt, which we were set for that, and we are getting 2 ampere of current on that circuit. And here is the power factor measurement of the circuit, which is indicated in the first figure on the power factor display, which is 0.9928, which is nearly to the unity power factor. And we also have done the THD analysis of the input current. And from the figure, as we can see, the red colored wave between the blue one is taken for the FFT analysis. And for that circuit, we are getting total harmonic distortions of 5.43%. Here comes the conclusion. The flyback converter operations and power factor corrections was evaluated through this project. The design of an AC to DC multi-output based flyback converter for power factor corrections was also done, and we have observed the power factor correction operation with two types of loads, as I have mentioned in this presentation, which was inductive load and resistive load. The system corrected power factor was achieved to unity, and which was 0.9928, and the total harmonic distortions of the input current was 5.43%, and the aim was achieved to correct the power factor and along with that to deliver the multiple output using the flyback converter. In the upcoming semester, the same circuit will be improvised to replace that switch with a GAN switch and to leverage the optimal performance of GAN switches at a higher frequencies and implementation of multi-output flyback converter will be considered. Thank you so much.